All right, good afternoon. How's everybody doing?
Good afternoon, doing just
Excellent. All right, so I think I figured out why the first recording Tuesday didn't work, so hopefully we'll get the full 2 hours of recording this time, but we'll see. It's always a little tricky with computers. So questions. How's the lab going? Any troubles, concerns?
I might have to redo the entire lab, restart the process. So I keep on getting some kind of error code, but maybe during the 2-hour lab time, maybe I could ask some questions if I run into something.
Yeah, definitely. Really quickly though, what kind of error code? Is it when you're trying to run the software? Is it when you're assembling? Is it when you're debugging?
At this point, I'm not really sure because I did it last night.
Okay.
But I'll just get into it after this 2-hour lecture, and then I'll see how far I get.
Okay. Sounds fair. All right. Any other questions, issues? All right. Well, let's get into it then. So I want to get into the heart of assembly language and looking at programming in assembly language, and I'm going to post some homework after class. So first thing, I've pushed the homework back one class already, so the first homework won't be due until a week from today. Okay, so I'll post homework right after lecture, and then you'll have a full week to do it, including next Tuesday's class to ask questions about it and stuff. But we didn't really go through anything substantial on Tuesday as far as the homework sets go, so that was all basically lab focused. So we're going to start talking about how we actually program a microcomputer. So again, this course is a hybrid. It's a combination of hardware and software, okay? And some people are kind of, geared towards thinking about software. They love software. They love writing code. They don't like dealing with resistors and voltages and KVL, KCL, and all of that stuff, right? Some people are the opposite. They love dealing with the hardware. They love putting things into proto boards and taking voltage readings and so on. And they get kind of iffy about writing code. This course really brings both of those together. And we're going to combine those together in a profound way in just a little bit. That will hopefully help with whichever way you're sort of geared, will help you make more peace with the other view of the world. Let me start off by telling you probably the most important thing you need to keep in mind in this course, okay? And that is, assembly language programming can be really annoying. It's really frustrating. It's going to make you upset. It's going to make you angry. It's going to make you ask, why are we doing this? Okay? Let me give you an example. Imagine that you have a butler who works for you, and this butler will do anything that you ask perfectly, right? Without tiring, without complaint, without question, they will do exactly what you tell them to do. Sounds like a great setup, right? But here's what happens. You come home one night and you say, I'm really hungry, I would like some dinner. And butler says, very good, ma'am, and disappears. And an hour later, you're still sitting in your chair and you're still hungry, and you see the butler out in the garden, and you say, hey, is my dinner ready? And what does the butler say? You didn't ask me to make dinner. You just told me that you were hungry. So you say, okay, you're right. Please make me dinner. Very good. What would you like? I'd like chicken. Very good. Hour goes by, you see the butler in the garden again. You say, where's my dinner? Well, your dinner's in the kitchen. Because you didn't ask the butler to bring the dinner to you. Okay? This would be simultaneously a really valuable person to have around, but also really annoying, because you've got to tell them, I would like you to make dinner. I would like you to bring the dinner to me. And when they walk in carrying a chicken in their hands, you need to say, no, I want the dinner on a plate. And then when they put that in front of you, you say, no, I also want some silverware so I can eat my dinner, right? And you have to spell everything out in painstaking detail. That's what assembly language programming is, okay? This processor, this 18-pin chip, will do anything that you ask it to do. It will do it faithfully, it will do it tirelessly, it will do it without error. But you've got to be really precise in what you ask it to do. And more than that, you often have to tell it how to do what you want it to do. So now take this person who works for you, and you can't say, make me dinner. You have to say, prepare a chicken as follows. Now get a knife and cut an onion in the following way, right? And you have to tell every single step to get what you want. Well, if you can spec out exactly what this person has to do to prepare your dinner, then that's fantastic, right? But if you hope to be able to just sit back and say, you know, make me some lasagna, that's going to be frustrating, all right? That's what programming an assembly language is like. You're going to have to tell the system every single little thing that you want done, and you're going to have to tell it how to do those things. Because what this processor can do is pretty limited. It has 30 or so instructions to it, that's it. And especially if you're used to programming in something high level like C or Python or Java, this is a huge change in mindset. And you can ask, why are we doing this? Why do we have to work in this language where we can't even add two numbers together unless we break it down into 3 separate steps? The reason is because the language that we are using to talk to this computer is breaking our algorithms into pieces that are basically simple enough to be performed by the hardware directly. So in a high-level language like, you know, Java, when you say take this string, concatenate that string, and then send it through the network to a server, there's about a zillion things happening in that one line. Right? In assembly language, an instruction that we write will correspond to basically a single change in the state of the hardware. Effectively, one tick of the clock. Right? Microcomputer is just a big state machine, so there's a clock. Every time it ticks, the state gets updated. Instructions in assembly language basically correspond to one tick of that system. All right, so I want to start off by showing you a somewhat fabricated, well, it's completely fabricated, picture of what the inside of part of a PIC processor might look like. Okay, and I'm doing this because this is going to help us understand how to program our processor. So here's the data memory. All right, this is the stuff that's, you know, 8 bits wide. And there's 256, 384, something like that, locations in this data memory. All right, so it's a bunch of registers. Register is a set of flip-flops. This is a set of registers. And there's an address which says which register do we want to read. Okay, we talked about this on Tuesday. And there's an input which says should we be reading or writing the memory. So if we put a 1 in here, it means let's read from the memory. If we put a 0, it means let's write into the memory. And here's a data input line. And here's a data output line. All right, so if read is equal to 1, whatever address is going into here, data out is showing us the contents of that address in the memory. And if read write is equal to 0, whatever address we have going into here, the data going into the D input is being written into that location in memory. Okay, that's a very basic standard memory model. There's a lot of details on top of that, but this works for what we're going to do. All right, And over here we have an ALU, an arithmetic logic unit. You had a homework problem in 250 to design an ALU that did a few functions. Basically, an ALU it's combinational logic. It has typically a pair of inputs A and B, and it has an input that we can call function. And then it has an output, which we'll just call out. And these are multiple bits, so our ALU is going to be 8 bits. So we've got 8 bits going into A, 8 bits into B, and 8 bits coming out. And our function says, how do we want to produce an output from our inputs? And so we might do something like this. If our function is 0, maybe our output is just always 0. If our function is 1, maybe our output is A plus B. If our function is 2, maybe our output is A plus 1. If our function is 3, maybe our output is A minus B, and so on. Okay, this is the thing that does the processing of data. And we choose how we want to combine A and B to produce an output by specifying a function code. Right? And you can spell out a truth table for this, and it's just a big, huge combinational block of logic. Okay, we're not going to worry about what's going on inside here. We're just going to think of it as a logic block. All right, I'm going to make a special register, which I'm going to call W register, or working register. That's an 8-bit register. And this is always going to feed the B input of our arithmetic logic unit. And it's a register, so it has a clock. And so this is the output, and it's got an input. And you know, normally the contents of the W register comes on this output line, but if the clock ticks, right, changes from 0 to 1, whatever's on the input line gets loaded into the W register. So it's 8 flip-flops, right? D flip-flops probably. All right. Well, what's going to feed the W register is either the output of my memory or the output of my ALU. So sometimes I'm going to want to take my ALU and use that to supply a value for the W register. And sometimes I'm going to want to take my data from my memory and use that to supply the value. So how am I going to control this? I'm going to use a multiplexer. So this is a 2-to-1 multiplexer. And I'm just going to have a select line, which I'll call W select. We're building the inside of a microprocessor here. Roughly something like the PIC 18F1220. Alright, so W select chooses one of these 2 lines to go into the input of the W register, and then if we tick the clock, that value gets loaded in here, and the value of W reg always goes to the B input of the ALU. Alright, the A input of the ALU is always going to come from our data memory. And the data input to the data memory can come from one of 2 places. It can come from W reg, or it can come from the ALU. So we're going to use another multiplexer. That's a 2-to-1. And this is going to have a select line, which we'll call, I don't know, memory select. So this was W select. This is memory select. And I think that's a pretty good picture for our CPU. Now I'm only looking at data memory, okay? And let's suppose we want to do some instructions. So we've got our data memory. Let's suppose we have, you know, at location 80, we've got a variable called A. So A is an 8-bit integer. We've decided we're going to store it at location 80 in our memory. Okay, arbitrary choice. And let's say we want to set A equal to 0. Okay, this is what we, the programmer, want to do. We're going to write an instruction that the CPU is going to execute. And what that instruction has to do is it has to cause some things to happen inside the system. So here's what has to happen to set A equal to 0. We have to take the address of A, which is hex 80, and we have to put that on this set of address lines. So we set this to hex 80. And then we know our ALU can generate an output of 0 if its function select is set equal to 0. So we're going to put a 0 on this function input. And now the ALU is going to put a 0 out here. So we have a 0 coming into this multiplexer. We're going to set the multiplexer select line to choose this bottom line, which is a 0, to go to the data input of the memory. And then we're just going to hit the write line. We're going to put a 0 on this line, which says write. If we do all of those things, if we set up an 80 hex here, a 0 here, select the bottom here, and a 0 on the read-write bar, what happens? This 0 gets written into file location 80. And A is now equal to 0. Alright, suppose we have another variable, B, and let's just say that's at file location 81 hex. And let's say we want to set B equal to B plus 1. Well, we can put the value 81 on the address line, the address bus, and have this be a read, which means the contents of file location 81, the contents of B, will appear on D out. We can set this multiplexer to choose this line to go into the W reg, right? Or we can note that this contents of location B, right, is already going into the A input of this ALU, and there's a function in our ALU called A plus 1. So if I set my function select to be 2, this ALU will say take the value coming in A, add 1, put that on my output. And now we have B plus 1 coming along this line. Right, it's a variable I'm calling B, but it's going into this input. The output is this input plus 1. So this is B plus 1. Set your select to choose this, put that on your data input. Now if I just drop this write line to a 0, B plus 1 gets written into location 81. Okay, we can do this in a single instruction. Because a single instruction is able to set up the values for this address line, this function, this select, and control the read-write line. We can use a single instruction to do B equals B plus 1. Suppose I have a third location here. Let's just suppose it's at location 82, and I'll call that C. And I want to set C equal to A plus B. Okay, this is harder. I have an adder. If I make my function 1, I can add what's coming in here and what's coming in there. I can certainly request an 80 on my address, which will give me the value of A, and I can load that into here. But I want to add B, which is at location 81. I can't read two things from this memory at the same time. Right? The memory just isn't built like that. I can put in an address, I can read a value. If I change this address to 81, I'm going to read the contents of this variable B. So I have to use this working register. So here's what I'm going to do first. I'm going to set address equal to 80. Set read-write bar equal to 1, so I'm reading. And I'm going to take this output, I'm going to send it through this multiplexer. So I'm going to set W select to choose this line, so that my contents of this variable A goes into the input of my W register. And I'm going to tick my clock. And now A is going to be loaded inside W reg. That's all I can do for one instruction. So now I'm going to do another instruction, which is going to say, read the contents of B, so set address equal to 81, read write bar equals 1. So now the contents of B is coming up here, and that's going into here. And what's going into this port is the value of my variable A. So now I have A and B going into here. I'm going to set my function equal to 1, which says add these. So now my output is A plus B. Well, I'd like to store that at file register location 82, but I can't do that. I've set my address to 81. I can't read from 81 and at the same time write to 82. So I'm going to have to use another instruction to do the write. Well, in order to do that, I'm going to have to save this value somewhere. Where can I save it? I'm going to save it back in my working register. So I'm going to set my working register select multiplexer to say take the value of this line, which is A plus B, run that through, tick my clock, and now my W reg is going to be equal to A plus B. And then I'm going to do a third instruction where I'm going to set my address equal to 82, so I'm accessing C. I'm going to set this selector to take the contents of the W register A plus B and feed that through. So now this is A plus B, and I'm going to set read write bar equal to 0, which will say write this A plus B into this location for C, and now I've done that instruction. Okay, so what's the moral of this story, right? Very simple instruction. Take two integers, add them, store them in a third. Takes 3 instructions in assembly language. And the reason it's taking 3 instructions is not just because the designers were lazy or this was a cheaper chip. It's because the way that the architecture is set up internally, right? You can only do certain things at a time. And for example, you can't read 2 locations from memory at the same time, or you can't read from one location and write to a different location at the same time. So the architecture forces us to break this thing into these pieces. So that's part of our challenge in assembly language programming is knowing that we need to break things into pieces, knowing what pieces to break them in and how to do that. And this working register is going to be fundamental to everything we do because it's a holding place, right? We can read and we can write our memory at will, but sometimes you need to remember a value that you've read or that you've manipulated, and that's what the working register is for. And we can copy from memory to the working register, we can copy from the working register to memory, or we can manipulate memory in the working register in some way and either place that result back in the working register or into the data memory. Okay, that's about 3 weeks worth of this course. Okay, that one sentence. It was a long sentence. So we can read from the data memory, we can put it into the W register, or we can manipulate it, or we can manipulate the data memory with a value from the working register, and the result can go back into the working register or it can go back into the memory. Alright, so we'll come back to this several times. Questions so far? This is where I normally look at everybody in the classroom to see like if this is registering, but everybody's got an icon or a letter.
I'm just grasping it for now. I guess I just gotta get into it a little bit further and then ask quick questions along. I mean, just for now.
Okay, that's probably exactly where you should be, right? This is probably new for most people, and I don't expect this to be crystal clear, right, or even vaguely clear at this point. But we're going to come back to this repeatedly, right? So this is just the first time we're seeing it. but we'll keep saying the same things over and over, but I think they'll start to make more sense as we get further into this. So the other part of this is we can write assembly language instructions like the things you put into Lab 1, right? Clear F port A, clear F port B, move LW 0x7F, move WF ADCON 1. We can write those things. The CPU doesn't know what to do with those until we translate them into ones and zeros. And we looked at what we call the disassembly listing, and that showed the ones and zeros corresponding to these instructions. Those ones and zeros are the things that do this. Part of those ones and zeros say put this value on the address. Part of them say let's set the read write to a 1. Part of them say let's load this into the W register by ticking the clock. Let's set the function equal to 1. Let's set the function equal to 0, and so on. So we're going to practice breaking down instructions into binary the way that MPLab does. We're going to start doing that by hand, and we're going to see that all of these different pieces that have to be set up in the hardware, we get to control those with the ones and zeros. And assembly language is just a shorthand, so we don't have to write ones and zeros. We can write things that are more human readable to us, and will get more readable the more we practice. All right, and this is just what I'm going to call the data path. Okay, this is the data memory. We haven't looked at all at where the instructions are stored. There's a whole separate memory that stores the actual instructions. There's an address that changes, something called the program counter, which pulls out instructions one after the other. We looked at it really briefly on the data sheet Tuesday. But this is just what's going on with the data manipulation, moving things around. All right, so let me show you some examples of instructions. So we have roughly 5 kinds of instructions: byte-oriented, bit-oriented, literals, controls, and byte-to-bytes. Most of our instructions are 16 bits, and they come with pictures that show you how the instruction is broken down into bits. Okay, we're going to work a lot with bit fields. We're going to see a number like this. Right, a 16-bit number like this, and we're going to break it up into a series of smaller numbers. Typically, we're going to look at these 8 bits, and they're going to mean something, and maybe these 6 bits are going to mean something, and maybe this bit means something, and that bit means something. Okay, so this table in the data sheet 20-1, which you'll look at a lot, shows you how, for what's called a byte-oriented instruction, you can interpret the 16 bits. In particular, the first 6 bits is something called an opcode. This bit is something called the destination bit, that's a D. This is something called an access bit, A. And these low 8 bits are called the file register, or F. Alright, so general thing to keep in mind about programming. Most instructions specify an operation. Okay, so there's an operator, there's a thing that you want to do: increment, decrement, add, subtract, and so on. And then an operand, which is the thing you want to do the operation to. Okay, this is a verb, this is a noun. In particular, it's something like a direct object. Right? We're doing something to that. We're operating on an operand. Okay? And the operator is specified by an opcode. It's coded a bunch of ones and zeros whose particular pattern corresponds to a particular operator, a particular thing we want to do. So this first set of instructions that we're going to be talking about are called byte-oriented instructions, and they have 6 bits worth of an opcode, a verb, right, an action that we want to take. And the main operand is specified by these 8 bits. What are these 8 bits? They're an address in the data memory. So the data memory is called, entering the data memory is called a file register. It's kind of a peculiar terminology, but these registers in here, they're called file registers in the language of PIC processors. So this would be file register 80 hex, this would be file register 81 hex, 82 hex, and so on. And these 8 bits in instruction specify the address of the thing that you want to operate on. So when we say set the address to hex 80, and let's read from that, and let's store the result in the W register, what we're saying is put 80 hex 10000000, that's 80 hex, into these 8 bits of the instruction. We're going to ignore the access bit for a while. Okay, just don't worry about this A bit. But the destination bit, if I want to write my result into the W register, I set this D bit to be a 0. If I were to set it to a 1, that would say write it back into the memory. So what is this destination bit? It's controlling whether the output of this goes into the W register or the contents of the W register goes back into here, and we say write the memory. So there's an action we want to take, there's what we want to take it on, and there's where we want to store the result, either back into the memory or into the working register. So 6 bits for an opcode. How many different instructions can we specify with 6 bits? Pretty close. You got a formula, maybe? What?
I just did 6 squared.
Oh, okay. Other way, 2 to the 6th. So if you have 1 bit, you have a total of 2 things that you can specify, a 0 or a 1. If you have 2 bits, you can specify 0, 0, 0, 1, 1, 0, or 1, 1. That's 4. If you have 3 bits, you have 8. This is 2 to the 1st, 2 squared, 2 cubed, and so on. So 6 bits, it's actually 2 to the 6th. So that's 64. So 64 different opcodes we could specify. We don't use all of them. There's really only about 30-some instructions in the PIC processor. Destination bit is a 0 or 1. File register can be any 8-bit pattern. So 8 bits, 2 to the 8th, that's 256. And that's all the random memory that we have in our PIC processor. 256 8-bit variables. That's it. So you can have 256 variables in your C program, assuming that they're each, no bigger than a character. All right, so opcode, destination bit, file register. So let's look at some opcodes. So table 20-1 lists all of your instructions. And the first chunk of them are these byte-oriented operations. And it's less than a whole page. But for example, CLRF, clear file register F, that gets coded with an opcode of 011010. And then this 7th bit is supposed to be a 1. And then the A is, we're going to ignore A for now, and then 8 bits of file register. Okay, what does clearF do? It says set the contents of a file register to 0. So when we wanted to say here in the beginning, let's set file register A to 0, we could code that in assembly language as clear file register A. And as long as somewhere we've told it that A is at location 80, right, this will clear this location in memory when that instruction executes. And so we can use a statement in the beginning. We can say A equals hex 80. Or in lab 1, I think it was done with a define. Right, but this is just setting up a symbol, which I'm calling A, as a stand-in for 0x80. So this instruction is really saying clear file register 80, which will cause all this stuff to happen. Put an 80 on the address, set the ALU to output a 0, set this selector to take the output of the ALU, put it into the data input, and set the read-write line to 0 to write that 0 into location 80. And everything the system needs to know to do that is contained inside these 16 bits. These 8 bits contain hex 80. And this particular bit pattern is unique. It only appears in this clearF instruction. So as soon as the CPU sees this pattern of zeros and ones, it knows it should set up, you know, the clock line and the ALU function and all that other stuff. Alright, set B equal to B plus 1, and let's suppose that B has been set up to be hex 80. So somewhere we said B equals 81. Set B equal to B plus 1, well, there's a special instruction for that. It's called increment file register. So in assembly language on the PIC, a semicolon starts a comment. So anything that comes after a semicolon is ignored by the assembler. So we can just write stuff there to help us know what's going on. So my comment here is I'm setting B equal to B plus 1. INCFB is my assembly language instruction. And when that gets assembled, INCF right down here has an opcode of 001010. And then the next bit is this D bit, this destination bit. And remember up here, the destination bit should be 1 if we want to write the result back into the file register. So since I'm trying to do B equals B plus 1, right, I would set this destination bit to be a 1. Access bit will ignore, and then the file register, that 8-bit, would be the 8 bits corresponding to hex 81, because that's the address where I stored B. Alright, now I want to do C equals A plus B. And let's suppose, you know, we also set up C to be 82. Okay, these are locations. This is not the value of C. This is where C is stored in memory. I'm saying I'm going to use this location, hex 82, for my variable C. So now I want to set C equal to A plus B. Well, if we look at our list of instructions, there's some things that have add in them. There's add WF, add WFC, and add, well, that's it. Add WF and add WFC. This says add the W register and F. This says add the W register and a carry bit and F. Okay. Well, we want to add the W register and F. Right, so our approach to this was to take A and load that into the W register, and then add the W register to B, and save that back in the W register, and then copy the W register into C. Alright, so first step is to move A into the W register, because we can't add 2 file registers. There's no instruction which says add F and G. It's just W register and F. So first thing we ought to do is move one of our numbers into the W register. Well, there's an instruction move file register, right, which says move file register. Here's the file register number, but we have a destination bit. If I make that a 0, that'll say move the file register into what's D equals 0, meaning the W register. So my first instruction is going to be move file register A 0. And this says copy A into the W register. These instructions are traditionally called moves, but they're really not moves, they're really copies. Alright, so this will copy A into the W register. Now we can use our add instruction, which says add the W register and the file register. We can specify any file register we want. So I'm going to say add the W register to file register B. So this takes the contents of W register, which is A, and adds B. But remember, we need to take that result and we need to store it back into the W register so that in our next instruction we can say take the W register, write it into location 82. So we need a destination bit, which is 0. So this says copy this into the W register. And then our third instruction is going to say move file register. We want to move the contents of the W register into memory. There's a special instruction for that. It's move WF. So move the W register to whatever file register we specify. So here we're going to say move W register to the file register C. So now we've done C equals A plus B. Alright, so we don't need to keep going back to this, we don't need to keep thinking about this, but it's in the back of our minds, right? If you're trying to add two numbers together directly and you're looking through your table and you can't find an instruction for it, you can't find an instruction, right? Come back and think about what am I asking the machine to do? I'm trying to read two locations from here and send them to the ALU. Oh, I can't do that, right? Think about the W register. More often than not, that's going to be the answer to your question. Use the W register. And there's a bunch of instructions that work with the W register, multiply W by F, move W into F, add WF, and so on. And almost all of these instructions can take their result and put it back into the W register. Right? That's why we have this destination bit. We can either put the result back into the file register or we can put it into the working register. Alright, so let's try coding some of these. So move F A comma 0. Let me take a look at the move F instruction. So it says 0, 1, so I'm looking at this line right here. I can't highlight this for some reason, but right above where my arrow is. So move F is 0, 1, 0, 1, 0, 0. And then the 7th bit is the destination bit. Okay, and that destination bit, that's what this 0 is. Okay, I want to go into the W register. And the last bit is the access bit, which I'm just going to make it a 0 for now. And then these lower 8 bits are the address of the file register. So I'm trying to move file register A. A is hex 80, so this is going to be 80 hex, which looks like an 8 followed by a 0. Okay, add WF has an opcode of 001001. So I've written out 001001. Followed by a destination bit. The destination bit is again a 0. And then an access bit. And then the 8 bits specifying which file register we want to add to the W register. So in this case, we're doing B, which is file register 81. So this is 8 followed by 1. And then our third instruction is move WFC. So move WF has an opcode of 0110111, followed by an access bit, followed by the file register. So move WF, there's the opcode, there's the access bit, and the file register is C, that's hex 82, so there's an 8, and there's a 2. So if I were to write this as a hexadecimal number, 0101 is 5, 0000 is 0, 1000 is 8, and 0000 is 0. If I were to write this as a hexadecimal number, this is a 2, a 4, an 8, and a 1. And if I write this as a hexadecimal number, it's a 6, an E, an 8, and a 2. So these blue lines, this is assembly language. These lines below them, the ones and zeros, that's machine language. Okay, assembly is human readable. So that's assembly code. Machine code is the ones and zeros. And sometimes you wonder, is machine code in binary or hex? Well, that's not really a well-formed question. Machine code is simply this pattern of bits, but we can represent it with ones and zeros, we could represent it with hexadecimal digits, we could represent it with dots and dashes. Right? These are representations of binary information. The binary information itself, that's the machine code. Alright, so let's do a 5-minute break. I'm going to fire up MPLAB and type in some code while we're stretching our legs. We'll come back in about 5 minutes, take a look at this code assembled, and then we'll start plowing through a whole bunch of assembly language instructions. Alright, so I'll be right back.